So 7.7 is the application of 7.6. So what you just took your drill on, we're going to need to use that as we solve these problems. So we have some strategies. There's not necessarily set steps, although you will only see the same similar types of word problems. So my first suggestion is don't panic when you see word problems. They're not anything crazy. If you read them all at once, it might be overwhelming. But we're just going to go through sentence by sentence. And we're going to read through and focus on the question. So if you know what you're looking for, it can be sometimes easier to pull out that information. We're going to use number 3. We're going to create a table to organize all of our information. Remember, sometimes there's extra information. Then we're going to set up and solve our equation and make sure our answer makes sense and give it a label. And then you've got 2 cartoons to help you, again, go with number 1, don't panic. So how I see math problems. I love this when I write it. If you have 4 pencils and I have 7 apples, how many pancakes will fit on the roof? Purple, because aliens don't wear hats. I've taught a lot of developmental math here, and that's how I feel like some of you read these problems. It just seems like a collection of random bits of information, and the answer's nowhere related. But it all goes together. And then algebra, this is the one. You guys aren't so bad. My next class is all over me, but I'm never going to use this. Algebra class will be important to you later in life because you're going to have a test 6 weeks from now. Well, yours is next week, but it's all relevant. All right, so let's look at our problems. The first type of problem, we're going to go over needs or distance equation, which you've hopefully seen this somewhere before. You will certainly see this equation after this class, and that's that distance is rate times time. So the way you usually see this written is D equals RT. Distance equals rate times time. So if I'm driving 30 miles an hour for 2 hours, I've gone 60 miles. You just do 30 times 2. So your rate times your time. The way we're actually going to use this in our problems is we're just going to rewrite it by dividing both sides by the time. Oops, sorry, we're not dividing by time. We want time. We're dividing by the rate. So the way we're going to do it is just, this is an 082 topic, rewriting a formula. We just solved it for time is distance over rate. It's just a rewriting of that first equation just by dividing both sides to solve for time. So that's how we're going to use the distance equation. We're going to talk about it in terms of time. Just take your distance divided by your rate. So that's like if I went 90 miles and I was driving 30 miles an hour, how long did it take me to get to my destination? So I'm driving 90 miles, that's a distance, 30 miles an hour, it would take me 3 hours to get there. That's what that equation means. You just take whatever your distance is and you divide it by your rate, and I'll tell you how long the trip was, time-wise. So if I drove 90 miles, did 30 of that every hour, 30 miles per hour, it would take me 3 hours to do that trip. That's your distance equation. We're going to apply that to a couple of different types of problems. So here we go. First problem. A car travels 350 miles in the same amount of time it takes an SUV with a trailer to travel 150 miles. Let's stop right there. Tell me everything you know from that sentence. Okay, car. Cars goes how far? So cars distance is 350 miles. It's a piece of information. What else do we know?
The SUV with the trailer travels 150 miles.
Okay, so the SUV's distance, 150 miles. What else do we know from that sentence? There's some other key piece of information in there. We're not going to the second sentence. We're still in the same amount of time. So that doesn't give us a number. It doesn't give us a quantity, but that's a piece of information that first sentence gives us. So we know that the time is the same. there any questions on just, again, we're just making a little summary list of everything we know to see what's going to help us later on. Get it out of that sentence form and just into little, this happened, this happened, this happened. Everyone okay with where we got all that information? Again, you're going to overthink these just piece by piece. That's what we know. Car's distance, they went 350 miles. SUV's distance, 150 miles. Those are easy to pick out because they're numbers. The other key here is that the time was the same. So let's read the second sentence. I guess it's really the only other one. We'll stop at the comma. If the car is traveling 40 miles per hour faster than the SUV and trailer. So miles per hour, if we're thinking about, we're going to be using this equation. We've got our distances. Is the 40 miles per hour going to help us with the time, or is it going to help us with the rate? Rate. Miles per hour is a rate. It's how fast you're going. Now, it doesn't say it's going just 40 miles per hour, though. It's going 40 miles per hour faster. So we don't know how fast either one's going. We just know one in relation to the other. So now we've got to think about, okay, let's try to get some speed. Or we'll rate. So the car's rate and the SUV's rate. Those are the other pieces of information we can get out of this. So the car is traveling 40 miles per hour faster than the SUV. So let's think in hypotheticals. So this is just, we'll call this what if. So the car is going 40 miles per hour faster. What if the SUV is going 30 miles per hour? How fast is the car going? 70. Why 70, Devin? It's 40 miles per hour more. So 40 per hour. So if I'm going 30 in my SUV, and I know the car is going 40 miles per hour faster, it's got to be going 70. Okay, let's say the SUV is going 50. How fast is the car going? Is the SUV is going 50? 90. They're hauling. So it's just 40 miles per hour more. Now, let's say we know the car is going 80 miles per hour. So it takes a little more thinking. The car is going 80. How fast is the SUV going? 40. Why just 40? 40 less. So if you're told the car to get to the SUV, we know it's going 40 miles per hour slower. That's not how it's worded in the problem, but it's something that we know. If one's going faster, the other one's going that much slower. So you can go either way. If I give you an SUV rate, you just add 40, you get the car speed. If I give you the car speed, how do you get back to the SUV? Subtract 40. Now, either of those are appropriate approaches. So what we have to do is decide which one we want to be X, the SUV or the car. It doesn't matter because we just saw you can go from the SUV to the car or from the car back down to the SUV. Now, I usually choose, personally, the one that's smaller, just because I like addition over subtraction. It doesn't matter. So I generally prefer addition over subtraction, having to do with negative numbers. So I personally would choose the SUV to be X. So whenever I give you the rate, the speed of the SUV, how do you take that and get it up to the car's speed? What do you do to the SUV's number to get it to the car? Add 40. So you start with the SUV's rate, which was X, and you add to that 40. So no matter what speed I tell you for the SUV, all you do is take that number and add 40, you've got the car. Now, let's just say, again, I'm going to put this in the what if. What if we said the car was X? How would we go from the car speed back down to the SUV speed? Subtract 40. So this is a perfectly acceptable alternative. So you could use, if you want the car to be X, you just take X minus 40 for the SUV. Either one of those will work for this problem. Again, I just like this way because I'd rather positive numbers. So that's really the hardest concept, I think, in this problem. Are there any questions? And when you're given something relative to the other, try some examples in numbers, see if you can find the pattern. Like if I start with the SUV, just add 40, gets me up to the car speed. So let's organize all of this information. This is the make a table. So we have the car, the SUV, and the things we know are the distance and the rate. So the car's distance was 350 miles. The SUV's distance was 150 miles. The car's rate we said was x plus 40, and the SUV's rate we're going to use is x. Now the only other column we have to fill in if we're using our distance formula is time. The only thing we know that's true about the time is that they're equal. But we need something to fill in our table. Something to put here for time. So if, yeah, Anna. So if you're going to do x minus 40 for the SUV, then you'd put just plain x for the car. You'd either do this or this, one or the other. And it will work out to be the same. Any ideas of what we could put in the time box? We don't have any more information from the problem, but we do have a distance and a rate. Maybe something on this page? Time is the distance divided by the rate. That's why we started the whole discussion with that. We can always represent time as, let me pull this down. Time is the distance divided by the rate. And that just comes from that distance equation. So for the car, that's going to be 350 divided by x plus 40. And for the SUV, we're looking at 150 divided by x. Is everyone okay with where that came from? So on your homework, you're going to have to set this table up. It's going to be something similar. Someone's going faster, distances, that sort of thing. Dennis. The 150 was given to us in the problem. So up here, it said the car's distance was 150. Sorry, the SUV's distance. SUV with a trailer travels 150 miles. That was a given in the problem. So now we've got all our information organized. Our question is, what is the rate of each? So what we're looking for is this column right here. There's one piece of information that we haven't put into the table. It didn't really go into the table that we took out of the first sentence. What do we know is true about their times? It's the same, which mathematically means they're equal. So we said right here the time is the same, which in math, same means they're equal. So I'm going to take the time the car traveled and set it equal to the time for the SUV. Because our problem says the time's the same. The times are equal. So this is our car time is equal to the SUV's time. Because the problem said they're the same. Now we gotta solve that. Which should be something we know how to do from 7.6. So first thing I need, LCD. What's my lowest common denominator? X and then x plus 40. Need them both. What else should I list before I start solving? Restrictions. What's my restriction for x plus 40? What value can x not be? 0 and negative 40. So the monomial x has a restriction of 0. So if I substitute 0 in, I'm going to get a denominator of 0. My restriction here is negative 40. So I do negative 40 plus 40. It gives me 0. I don't want zeros in the denominator. So x can't be 0 or negative 40, which hopefully it's not either of those anyway. So that means the SUV is either not moving, which we know it's moving, or it's going negative 40, which can't have a negative rate anyway. Dennis. You always should. There are some problems where it might matter in the applications. When you're solving a rational equation, you should list your restrictions to make sure your answers fit. So like back in 7.6, we listed restrictions for every problem. So you really should list them if you remember to check them, or like I said, none of these should come up anyway. It's not as important here. All right, how do I get rid of the fractions? Multiply by my LCD. So I'm going to just take each of these and multiply it. Oops, I got that one wrong. Multiply it by x plus 40. Now your other option here is to cross multiply. I'm not going to do it that way just so we're consistent, but if you look at that and say, oh, I could cross multiply, and you know how to apply that, it works. But I'm just going to solve this the same way we did the problems last time. All right, so in this first term, what cancels? X plus 40, so I'm left with 350x equals, and what's going to cancel out on this side? X. And what am I going to have to do to bring that down to the next line? Distribute. So it's 150 times, so I need your parentheses, x plus 40. So we're going to distribute the 150. So we're looking at 150x plus, I think it's 6,000. What type of equation is this? Linear. So it's linear. Just going to get my x's to one side, my numbers to the other. So I'm going to bring the 150x over. So I have 200x equals 6,000, and then divide both sides by 200. You get x equals 30. Now we've got to see, does that answer our question? Is there something else we've got to do? So our question, let's go back. What is the rate of each? So if I look, this is why a table is also helpful. If I look at my table, what does a plain x stand for? If I go to my table, where do I see just the x? It's the SUV's rate. So x is the rate of the SUV. So the SUV then is going 30 miles per hour. That's x. But the question is, what's the speed of each? So if the SUV is going 30, how fast is that car driving? 70. Oh, that was an original what if, yes. So I think you have two like that on your homework questions. They're all going to be very similar. It's being able to pull out that information, which again is why for your review I'm going to create another sheet that just has some extra word problems so you can practice setting them up. So once we get down to this part, it's all from last time, but it's being able to organize our information, which is the new skill. All right, let's read our next question, which you're going to think sounds totally unrelated. It's completely related. So in Stillwater, a boat travels 18 miles per hour. It takes, I should say the, not he, it takes the Same amount of time to travel 33 miles downstream with the current as 20 miles upstream against the current. What is the rate of the water's current? So do you see any similarity between our information given in this problem and in the last problem? Okay, miles, so we have some distance. So why don't we start pulling out information that we know? So let's go with some distances. Now and you'll see current problems. They're going to be boats traveling with and against the current or planes traveling with and against the wind. So distance, I'm going to do with the current and against. Which it tells us with the current is downstream and against is upstream. You could also use that for your words. So with the current, what's my distance? How far did I travel? How many miles did I go with the current, which is downstream? 33. 33 miles. All right, against the current, which I'm told is upstream. What's my distance? Okay, 21 miles. All right, let's see if there's any other information that we know. Oh, say it again, Ayana. Same amount of time. Common thread with our last problem. We're told that the time is the same. That's really how the last problem is very similar to this problem. Is there any other information in this problem that we're given? We know something about distance. We know something about time. What's the only other thing that's in our equation, our distance equation? Rate. But we're only given one rate. We're just told that the boat in still waters is going 18 miles per hour. But you see, we know a little something about everything in our distance equation. We've got our distance. We know something about the time. We don't know what it is. And then we know that the rate of the boat is 18 miles per hour. Now, the next piece of information is not something I expect you to have known just by reading this problem. But it's something I'm telling you applies to every single one of these problems. Every single going with and against the stream, whether you're a boat, a plane, and you see these problems a lot. This is important. When you're going with the current, what you do for your rate is you take your boat, your plane, whatever, and you add, we're going to use x, and say x is the rate of the current. So, and it depends on how familiar you are with like rushing water. So if I'm in a boat and I'm going downstream, which means the water's helping push me, do you think I'm going to be going faster or slower than when I turn around and the water's working against me? You're moving a lot faster. That's why we add the current, because the current's helping you move. It's helping you get there faster. Versus if I'm going against the current, it's slowing me down. The water's slowing me down. So you take the boat speed and you'd subtract the rate of the current. And that's just in all of your current problems. When you're going with, it helps you, you add it. When you're going against, it's slowing you down, you subtract it. Not something that you would have known before you did this problem, but something that I'm telling you is a common, comes up over and over and over. So when you're going with, you add. When you're going against, you subtract because it slows you down. So let's try to organize our information then. So let's see. We've got with the current, against, and distance, rate, time. So I said, it doesn't sound like the same problem as before, but we're going to organize everything the same way. So distance is the easy part. It's explicitly given in the problem. When you're with the current, you go 33 miles. When you're against the current, you only get 21. When you're going with the current, you take the speed of your boat. What's the speed of our boat? 18. And the current's helping you, so you add it. when you're going against, you take the speed of your boat again, but you subtract the current. So this part right here always looks the same except for the sign. Anna. What do you mean? No, when you have current problems, they both have the speed and the current in them. Whenever you have a current problem, it's your speed plus your current, your speed minus your current. That's just how this column always works. Can someone set me up the time with the current? I want to set up now the time with the current. 33 divided by 18 plus x. So time is just our distance over our rate. And then, so what's my against the current? 21 divided by 18 minus x. And it's the same key as the first problem. What do we know about those two times? They're the same. They're equal. So we're just going to take 33 over 18 plus x and set it equal to 21 over 18 minus x. So what's my LCD? 18 plus x, 18 minus x. And just for consistency, let's list out our restrictions. Positive and negative 18. So negative 18 for this first one, because 18 minus 18 is 0. And then positive 18 for the second one, because 18 minus 18 is 0. So x can't be negative 18, positive 18. That would be quite the current if your current's going 18 miles per hour. How am I going to clear my fractions? Multiply by your LCD. I'm going to take each fraction, this is back to last class, 18, and multiply by my LCD. And what's going to cancel over here? 18 plus x, so I have 33 times 18 minus x. So we're going to distribute the 30, oops, not there. Distribute the 33, and I got 594 minus 33x equals, cancel the 18 minus x on the other side, distribute the 21, 378 plus 21x. What type of equation? Linear. So get your x's to one side, your numbers to the other. It does not matter which way you go. I'm going to take my x's to the right this time just so they're positive. Does not matter. So I have 594 equals 378 plus 54x. Divide through, or sorry, subtract 378. 216 equals 54x, and divide by 54. So I get x equals 4. And then make sure you've answered your question. So the question is, what is the rate of the water's current? What does x stand for? We have a lot of stuff written here. X is the rate of the current. So in this problem, when we're done, we have our answer. We don't have to do anything else. Now, if it asks us, like, what's the boat's speed with and against the current, then we'd have to go back to our table. But it just wants to know what's the current. That's x. So 4, and I guess we're in miles per hour. Questions? So those two problems are similar. They don't look it, but they are. So we're not going to get through both of these next one, but they're, again, the same two problems. So we'll do one of them. And then I'll write out and post the other one to miscellaneous handouts in Blackboard. So you can try it yourself first, extra practice, and then check it. So our last type of problems are, these I think always sound like 90s sitcom, kids sitting down doing their homework at the table. People working together to complete a job. So we're going to create a table, and this describes how that table works. So here's our first problem. Greg can paint a room alone in 3 hours. His brother Philip can do the same job in 5 hours. How long will it take them to paint the room together? And it sounds like one of those TV problems. So you need a table for work problems. So let's make our table that includes both of our people or things. So we've got Greg, we've got Philip, and the other thing that we want to know is them working together. So Greg, Philip, together. And the only thing we're given in this problem is their time. So how long does it take Greg to paint the room? 3 hours. Philip, it takes 5 hours. Do we know how long it takes them working together? No. How might we represent something we don't know in math? X. You can't just add their times together. If you add their times together, it says they're slower together than they are apart. So that's our unknown, that's our X. The other thing we need is our part per hour. So let's think about this. Let's think about Greg. Let's say this is the whole job. And it takes him 3 hours. So that means he does a portion the first hour, a portion the second hour, a portion the third hour. We're assuming he's going at a constant rate. How much of that in a fraction does he get done in the first hour? 1/3. Now, if you think similarly for Philip, if we had the same block, but we divide it into 5 slices because it takes him 5 hours, how much does he get done in 1 hour? 1/5. This column here is always, we call it 1/. So it's just 1/, whatever their time was. So if it was 6 hours, 1/6. If it was 9 hours, 1/9. If it was X hours, what do you think we put in this column? 1/X. This column is always 1/, whatever you had here. Whether it's an X, whether it's a number. The other thing that's consistent that never changes in these work problems is you take the people working together, you add them up, and it equals their together time. It's never subtraction. It's always you add them together because they're working together, and it equals together. So we're looking at 1/3 plus 1/5 equals 1/X. Now we still have a couple minutes, so I'll give you an option. Do we want to solve this or do we want to set up the other one? Because this solving you should be able to do. Set up the other one. Let me give you the answer to this one. I'm not going to go through all the steps. What's your LCD here? 15 won't clear them all. 15x. So if you use the LCD 15x, you should get down to x equals, you get 15/8, which your problems will tell you to round or leave them as a mixed number. So you'd say 1.9 or 1 7/8. So you'd multiply each one by 15x, and this is what you should get for your answer. I'll write up all of the steps and post them on Blackboard. But let's get the second one set up just so we can see the consistency of these problems. So it gets very hot in Maryland, and to help your dog cool down, you get a kiddie pool. It's fantastic, doesn't help me. One pump can fill the pool in 8 minutes. A different pump can fill the pool in only 5 minutes. You're going to be late to work if you don't leave in the next 2 minutes. If both pumps work together to fill the pool, how long will it take? Do you have enough time to fill it before you leave for work? Again, it sounds ridiculous, but what do we know? We've got 2 pumps filling a pool, which means they're working together. Yep, so pump 1, pump 2, and what's the last row I need? Together. What's my time for pump 1? 8 minutes. What's my time for pump 2? 5 minutes. What's their together time? X. We don't know it. Where's that 2 minutes come in then? It doesn't go in our table. It's going to help us answer the question, will you have enough time to fill it before you get to work? But it doesn't go in our table. Remember, I said sometimes there's extra information. 2 minutes to leave to work doesn't have anything to do with the pumps filling the pool. The other thing we need is our part per, in this case, what are we looking at? Minutes. Part per minute. So if it takes pump 1 8 minutes, what's its part per minute? 1/8. It's always 1 over. That is consistently 1 over. So 5 minutes for pump 2, part per minute. 1/5. Together times X, what's the part per minute? 1 over X. I told you they're all set up the same. You take whoever's working together, you add them, and it's equal to the together. So 1/8 plus 1/5 equals 1 over X. Then you can get your LCD, clear them out. I'm going to tell you that when you get to the end, your answer is X equals 3.1. You're going to have to round to 1 decimal place. I will put those directions on your test. 3.1 minutes. Our question is, will you have enough time to get it filled before you leave for work? No. That's where you need to know you've got 2 minutes to leave for work to answer that question. So give those homework problems a try. You only have, I think, 5 problems.